Andrea?
No, me.
Oh, you, sorry, Lisa. Go ahead.
Adam is gonna manage our little slide deck. It looks like a lot of slides, don't worry. A lot of them are just like similar. We're just trying to point out some things. So Adam, waiting on your questions. Okay. All right. Great. Thank you for the introduction. And so I'm really excited about this because these are some really tricky questions, and they're important, right, for understanding how disks evolve and whether or not planets can form, and if they do form. So what are these open questions that we're really interested in? So one is this relationship between the gas and the dust, which triggers which. And Alicia just sort of touched on it a little bit with the debris disks. You still have both in some cases, but you also see places where there's gas and no dust, or dust and no gas, even in the transition disk. So that's one open question. Another one is, what are the things that are driving the disk dissipation, and why sometimes you go from full disk to no disk very quickly, and in other cases you have disks that live for a long time. So I'm just going to do a quick overview of the disk structure. You guys had great talks this morning, so I think everybody's going to be an expert now. But if you go to the next slide, Adam, I just have a cartoon quickly, the kinds of things that we look at to understand this, what the disk structure is and how it dissipates. Joan and Lars talks had great examples and great detail, but just quickly, these are all the different components, right? You have a star that's not a tennis ball in the middle, that is a star, and you have the stars rotating rapidly. You have the accretion shock that Joan was pointing out. We have spots, you have all these different phenomena. And so we can observe these things and try to understand what's happening with the dissipation or the structure. Next slide. So for example, we look at the light curves and we can see all these different phenomena. We can actually take a power spectrum. The top panel there is just from K2. We take a power spectrum. We get that peak on the bottom there, the period of the rotation of the star. So you can actually pull out amazing information. And you can still see all this variability caused from all these things people have been talking about today and yesterday: the accretion flows, structure in the disk, the orientation, rotation of the disk, the accretion shock. So it's a lot of different components, a lot of things going on, very complicated. Next slide. So you can also look at the forbidden line emissions. So this is the forbidden oxygen 1 line at 6,300 angstroms. And this gives you these different components shown here for RW Auriga over just a fairly short amount of time. This is very dynamical. The components of this line are changing radically. So you have some component from the fast collimated jet, some from the different components of the disk wind. Next slide, please. And so you also get different diagnostics of the accretion itself. For example, from H alpha, you can see a huge amount of variability as that gas is going along these accretion flows onto the central star, and the variability in the accretion shock. So you get your hydrogen lines are changing in both their structure and their equivalent widths. And next slide. And then you have everything that we were just looking at this morning, the light that's the scattered light off these disks, up in the top middle there, so that you have the warm gas and the dust. You have the scattering off the dust, and then you have the ALMA, of course, from the millimeter and submillimeter, just the emission from the cooler dust further out. And then I put in here a little spectral energy distribution, just because you have the hands-on sessions going, and we've seen a lot of these today. It's just the amount of light at these different wavelengths, or the flux density at these different wavelengths. And I'm going to do a sort of the last slide. And right now, Andrea and Adam are going to go ahead and talk about the different sources of dissipation. So I'll come back to that spectral energy distribution.
Yeah, thank you, Lisa, and thank you to the organizers. This topic is very fascinating and very challenging because it's so complex and so much goes into it. But I was asked to focus in particular on my expertise, the evolution of inner disks. So in my first slide, I want to highlight, dive a little deeper into the discovery space that Joan mentioned in her talk, the one opened by high resolution spectroscopy of inner disks. And I want to briefly show what we are learning from from high resolution spectroscopy about the difference between a full quote unquote disk that now ALMA shows us to be carved with structures and the transition disk. Okay, next. So the first tracer I want to highlight is the fundamental CO emission at 5 micron. This is probably the most fundamental, really, and ubiquitous tracer of molecular gas in inner disks. And what we're learning is that full disks have high velocity gas, multiple velocity components, and complex line profiles with shoulders, as you see to the left, and the double peaks that remind us of Keplerian rotation. On the other hand, transition disks are way simpler, narrow lines and single components where the high velocity gas is gone. Next. Now moving to water emission between 3 and 30 micron. This is clearly the realm of JWST as it comes online. Even here, beautiful spectra and extremely complex and rich in full disks to the left. You see two extracts from 2.9 micron, around 3 micron and 30 micron. The water spectrum is extremely complex and rich in between those wavelengths. Once again, transitional disks are quite boring, if you like, or very much simpler. Flat, no water emission. Next. Another tracer, forbidden oxygen, that Lisa already mentioned. Recently, we have dived into distinguishing multiple velocity components. There are, in green, you see the high velocity components associated to jets, fast gas at hundreds of kilometers per second, and low velocity components related to MHD and photoevaporative winds that are probably dispersed in the inner disk, as I will show in the next slide. Once again, transitional disk, much simpler story or data, narrow lines, simpler structure that are possibly telling us of an evolution in the structure of winds. Next. And finally, the final tracer I want to highlight is H2 from HST in the UV. Here we see that molecular tracers, CO and H2, trace similar regions of the disk, again, broad lines and collocated from their similar line shapes. Transition disks show that as the dust is evolving, there is a radial stratification in the gas, where there is an inner region where H2 is still survives and CO is gone. So what's the big picture here that is emerging? That as dust is evolving in inner disk and being depleted and forming these structures here at the top right, the transitional disk that we see in the SED, as dust is dissipating, there is a strong physical and chemical evolution of the inner disk. And this is really new world and new discovery space for many of you probably here at this conference. Next, please. So in the second slide, I want to highlight two main topics that are extremely hot and developing at a very fast pace now. One is on disk winds, and the other one is the connections between inner and outer disk evolution. So next, for disk winds, they come in two flavors. The MHD disk winds are expected to drive accretion jets and have mass loss rates that are possibly as high as the accretion rates measured on the star. So this could be, MHD winds are extremely complex, as you see in this example from Romanova, but they could be a sort of a key that is connecting multiple aspects of inner disk structure and evolution. Next. The photoevaporative wind is the other flavor. They are expected to dissipate disk very quickly once they open a gap and to act only beyond a few AU around the solar mass star. And in the central bottom plot there from the review by Ercolano and Pascucci, you see the regime in the lower left corner where winds could explain the observations in terms of accretion rate and inner cavity sizes. All the rest of the parameter space has to be explained with other processes that have been mentioned earlier today, including binaries, planet formation, episodic accretion possibly. Next. All right, and another hot topic now that is developing very quickly due to available observations, ALMA and now soon JWST, is connections between inner and outer disk evolution. Here I show an example from a recent paper we published, and there is a new one, theoretical modeling these processes by Kalian, coming up soon, where we are investigating how pebble drift, that is a fundamental aspect of this evolution, is shaping the physics and chemistry of inner disks. I want to highlight we have an approved cycle 1 JWST program dedicated to this aspect, to study how water emission inside of the snowline is connected to pebble drift from the outer disk. Next and final. The other aspect that already came up earlier today is another aspect of connections between inner disk and outer disk. In particular, a big question is about how this large-scale structure that we see from ALMA and scatter light imaging may be related to structure that are yet unseen in the inner disk. And one example that was brought up, and another very hot topic, is the presence, possibly common, of misaligned inner disks from this work by Miriam. And here I stop. My 5 minutes.
Okay, and then I'll pick up to talk about a related topic. So one of the sets of major questions that we've settled on is what factors, both internal and external, drive disk dissipation, and more generally, disk evolution. So for example, we often study disks and planet formation in environments with relatively low stellar density, because those are the ones that are nearby and easily accessible to us. But many stars, maybe most stars, form in denser clusters with potentially substantial external influences by other stars on our picture of so far one star with a disk around it that is forming planets. Also, close to half of all stars are probably formed in binary star systems. And so there are probably a lot of different, mostly detrimental influences that might occur once you add another star to the system. And so I think a lot of this comes down to questions of timescales and which processes happen in what order. So I'll remind you of the main picture that folks have already talked about quite a bit so far this week. You have a core, so this shows the classical class 0 to class 3 system of thinking about protostars, what it actually looks like, and then the rough time scale over which we expect that stage to last or to stretch over. And so you have a core at the start, then you have a protostar that is surrounded by a disk and an envelope with quite a bit of the mass still in the envelope. But then eventually the envelope finishes dumping its mass down to the disk and then onward to the central star. And eventually you have just the star and its gas-rich protoplanetary disk around it. And then eventually the gas-rich disk is dissipated and we're left only with planets and with debris, small bodies and dust and whatnot. The solids that are left over after the gas is no longer there. Though, as we've heard a little bit of, even this is kind of a fuzzy boundary with some gas left for a while or re-liberated for a while. The timescales here are spanning roughly 10 to the 5 to 10 to the 7 years and beyond. So we can place various expected influences on this timeline, indicating when and if we can test which influences matter at different times we might observe the disk and planet evolution process. So to do this for binaries, then we might think about how, first off, we would expect if you have 2 stars there instead of 1, then tides from the binary should truncate the disk. We commonly say it'll truncate at about 3 times the binary semi-major axis, and around each star down to about 1/3 of the binary semi-major axis. So starting fairly early on and through this whole process, there are ranges of orbital parameter space where you just can't have stable orbits for the long term. After the disk is truncated, even in the parts where the disk continues to exist, you have planetesimal stirring. And so the tides of the binary will interact with the small bodies that are presumably colliding and we think growing into planets. And in a single star case, these collisions tend to be fairly gradual and calm. And so it's easy for a collision to occur where 2 small bodies collide, stick, and form something bigger. But if you have a binary system there, it'll be stirring up the orbits of these small bodies, making them eccentric, making them inclined, so that the collisional velocity is raised. And so this is a plot I'm including here showing impact velocity as a function of orbital radius for one specific system where they modeled one of the Kepler circumbinary planets, as it might have been at early times, showing that many of the bodies, rather than having a low impact velocity that results in accretion, will have a high impact velocity that results in erosion. You don't build your planets, you only grind them down. You also, potentially at the end of this process, can speed up the photoevaporation stage and speed up your dissipation of the disk. Even if you have space where you can make planets and you can make those planets grow and make planetesimal stick to each other, then the disk might boil away pretty quickly, because when you add a binary to this classical cross-sectional view that we've seen a lot of versions on over the last 2 days, then the binary is going to truncate the disk, open up gaps, and directly expose the outer disk to the photoevaporative flux of the central stars, which in single stars, the outer disk is probably largely, though not entirely, shielded by the inner disk, where the potential well is deep enough that even if you heat up the gas, it won't be driven out of the system. But if you expose the outer disk only by opening a gap, then everything that's boiled off of that outer disk is probably going to reach a state velocity and leave the system quickly. But then even if you manage to form disks within the possibly shorter time that you have to do so, then over the long term, then in-body simulations, like this one of the Alpha Centauri system, show that planets generally only stay stable for a fraction of all orbits, because you have long-term secular interactions between the planet and the binary, and across a large range of orbital parameter space, then they don't stay stable at all. And so they are kicked into one of the stars or out of the system entirely. And so you're left with this set of down selects or set of obstacles that seem to make for a very sort of discouraging picture of whether we expect to find planets at all in binary star systems. We still see a lot of disks and we see a lot of planets in binaries, even with a binary companion on the solar system scale. To pick an example, Alpha Centauri has a binary companion at the position more or less of Saturn. And yet we're still looking and trying to decide, does it have planets there or not? But there are a lot of other systems that do. And so I'll wrap up with sort of the general thought, how can we test which of these potential down selects are actually down selecting? And which of them matter, which of them don't, and how the details operate. And we can think about this in terms of observing different stages. If we want to see how fast do disks get dissipated, do any of them basically never even form, we can look at very early times, at protostellar disks during the class 0 and class 1 stage. If we want to look more generally at lifetimes, or if we want to ask, how does disk survival correlate with some other property of the system? For binaries, it might be eccentricity or mutual inclination. In a cluster environment, it might be how close is your nearest O star. We can be looking at protoplanetary disks. If we want to ask, did we form anything at all, then maybe we go to the class 3 stage after the gas-rich disk is mostly or entirely gone, but there are still solids around, and we can ask, do we see debris disks? Do we see evidence of even small bodies colliding with each other and releasing dust that we can then detect? Or we can go out to gigayears to old planetary systems, and we can ask, what is the occurrence rate of planets in binaries versus singles? And how does that correlate, or how do the planetary system properties correlate with the properties of the binary, or with the environment we think that the planet and the star formed in, or other questions? And so I want to cast this as us thinking about time as the critical parameter when we're constructing experiments. And when can we sample, how can we sample different times and what is happening at different times to reconstruct this story of going from a cloud of gas and dust in space to a star with planets or not? And now I'll hand it back to Lisa for the last part of our intro.
Yeah, for the last set of problems, I will go back to that spectral energy distribution. And if we just look at the near infrared and the mid infrared, so up in that upper left corner, there's flux density versus wavelength. And the higher hump on the left is from the star, it's the stellar photosphere. And then the additional hump at longer wavelengths, of course, is from a disk. And so one nice way, if you don't want to go and get a whole spectral energy distribution, one very compact way to get a sense of whether there's dust, warm dust in a system from a disk is you look at the colors. You can look at the K-L in the near infrared, you can look at K-N, which gives you a sort of a lever into that mid-infrared region. And that's coming in the sort of top right figure cartoon there. You can see the very warm dust, the warmest dust right by the dust destruction radius there, where you have the warm gas and you have the accretion flows kicking in. That's where you see your K-L color. And then you have K-N just a little bit further out in the disk. Of course, the distances depend on the stellar temperature and the disk exact shape. But what happens if we look at the K-L and K-N for a large sample in the lower left there? And this is using W3 from WISE, which is approximating the 10 micron N band, which W3 is closer to about 12 microns. So that's sort of a pseudo K-N on the y-axis and then log of age on the x-axis. And you can see if you divide these up according to whether it's a full disk, class 2 accreting disk, it's a transitional disk or an evolved disk. The ages, for one thing, all are very, very similar. If you do the statistics on those ages, they come out to be indistinguishable, whether they're the blue with the red or the turquoise populations in there. And so you find systems that have no disk that are very young, and you have systems that have a disk that are 10 million years old. And you also see in there this big gap, right, between K minus W3 or K minus N of 1 and 2 magnitudes. And so what's that? That is an indication of how rapidly you do this transition from a disk that's discernible, optically thick in the K minus N dust temperatures, to something that has no disk, at least at that particular radius and that temperature for the dust. And so that's a clue. There's very rapid processes going on, because what happens is things that have a disk that's discernible at K minus N, suddenly that dust goes away and you have no disk. And so those things zip through that gap, which is why we don't detect them. Another way of looking at this is to look at an HR diagram. This is work from Tom Allen, and he was looking at Ceph OB3b, and it's showing this low mass stellar population, and he used infrared excess to get the disk presence, and X-ray Chandra data to get the no disks on those blue points, and the red points, the ones that have disks. You can see they're overlapping in this HR diagram, both in age and mass. So there's something going on that sometimes dissipation happens very rapidly, and conversely, sometimes it goes very slowly. So last slide, please. So just to recap our questions: what is the relationship between the gas and the dust? Which triggers which? What factors, internal, external, binaries, nearby O stars, winds are driving the disk dissipation? And why do we have some disks that last for a long time and some that go very rapidly? So we would love to take your questions.
Thank you very much to the three of you. We do have some questions, a couple of them. So one says, does the time scale of the disk effects invoked by binarity scale with mass? And also, would we expect truncation to occur faster for a larger mass binary system?
Adam?
Sorry, I was
Maybe
switching
Adam, yeah.
back out of my screen share. So parsing the question. So I think at this point, we don't have as much of a handle on the mass lever arm of disks interacting with binaries. The general sense, I think, from the demographics so far is that there isn't a large effect in terms of, if you have a binary of a given semi-major axis, does it matter if it is 1 solar mass plus 1 solar mass stars, or 0.1 plus 0.1, or 1 plus 0.1? I think the lack of dependence on primary star mass and on the mass ratio is one of the features that we need to be keeping in mind as we think about our stories as to which of these effects matter or don't. It is worth noting that in general, as you go to much lower or higher masses, the binary semi-major axis distribution itself varies. And so this probably shows up as a second order effect in that there are more or fewer binary companions at a given radius. In that, say, low masses correspond to generally small binary semi-major axes. So you won't have a 50 or 100 AU binary of brown dwarfs in most cases. So that effect probably just doesn't really happen there. And so I already lost where the question was at in the Q&A.
Oh, I moved it to answered, yeah.
Oh, okay.
So if you go to answer it, it's at the end. But yeah, it says, yeah. It asks about the timescales.
Yeah, and so the general timescale, it's worth knowing for context, the timescales of disk evolution matter, or it's depend on the mass of the central object, in that lower mass stars tend to keep their disks for longer. It seems like G stars probably take a few million years to get rid of their disks. If you look at 10 million year old populations, then the disk fraction for M stars is still close to a half. And you see some around low mass late type stars even in 20 to 30 million year old populations, these very longest lived stars. And so there's an overall timescale dependence there that we've only just sorted out in the last 5 or 10 years. And I don't think we have a sense of we can't stretch the sample binaries along that axis in order to ask, is it a demonstrable signal that the higher mass binaries get rid of their disks more quickly? But yeah, that would be an interesting test to try, but it would require samples in several regions of different areas, or several regions of different ages. And so I don't think that sample quite exists yet.
Do any of you want to comment, Lisa or Andrea? We can also move on to the next question that asks if the disk can protect the planet from heavy cosmic radiation, which I assume is more related to an astrobiology question.
I think it to some degree it can, and to some degree, I mean, I think the rough number for cosmic ray bombardment of a disk, you ionize, you think about an inner disk, you're ionizing about 10 to the minus fifth gas molecules. So you have some charged particles, which is, you know, actually it's interesting, disk locking hasn't come up at all yet in these first 2 days, but disk locking is a phenomenon by which the purportedly the magnetic field of the star threads through the inner disk and actually locks the disk. And so you have that the cosmic radiation is key to this process, because you have to have some density of charged particles in that inner disk for that magnetic field to lock into the gas. And in that sense, absolutely, it's a requirement if disk locking is going on. As far as further out in the disk, I haven't thought about that. Maybe Andrea or Adam have, but I assume there is some degree of protection, but I don't think it's absolute.
Well,
Okay,
either way, and I think.
Sorry, go ahead, Adam.
So I think on the time scales where the disk is around for the first 10 million years, then protecting it from cosmic rays doesn't really matter for like astrobiology purposes so much. There's no life within the first 10 million years, we assume. Never say never. But I think it is, having the disk there is to some extent a prerequisite, at least for what the gas giants are doing, because like the temperature of the gas in the atmosphere is going to affect like how quickly can you accrete gas from the disk down onto a planet. And you basically expect to fill the Hill sphere or the virtual lobe of the planet almost pretty quickly. And it's just how quickly can you get rid of entropy in order to condense further mass down into the gas giant planet before the disk goes away, and then the whole mass heats up, and then the gas goes away shortly thereafter. But you need enough mass, presumably inward from there, to keep the disk relatively cold so that your gas giant planet can form. And so that might be one of the main impacts of having the disk there for shielding, is for atmosphere accretion.
Great, thank you. There was a question that was answered, but Andrea mentioned that it would be interesting to bring it up again. Why is there no H2O in the transition disk? The gas depleted inner cavity extends all the way to water snowline. Yeah,
sorry, I answered that in the chat, and so I got ignored.
Yeah, no, that's fine.
It was an early question.
Yeah.
But, no, I think it's interesting, and it demonstrates the power of using multiple tracers, because if you remember what I showed in the slides, by looking at the CO line and H2O lines, we see that CO lines are still detected in transition disks and H2O lines are not. So this goes back to what Karen was showing earlier today, exactly related to what Luke is asking in this question. This is the simple picture that we are thinking of, where the inner disk is evolves and is dissipated from the inside out. And this dissipation region reaches and goes beyond the water snow line, but CO is still detected because this CO snow line is much farther out. So it's pretty nice to see these two tracers that evolve together, but one at some point disappears because there is the water snow line and the dissipation has hit Now the water is no line, and then it keeps moving to larger and larger radii, and CO is still there, until it becomes, the disk at that location becomes cold enough that even CO in the infrared is not excited anymore. And so we lose inner disk dissipation from the infrared tracers at that point. But this is to say that early disk dissipation will be really the realm of JWST from the point of view of unresolved spectroscopy, right? And of the future ground-based spectrographs from the point of view of high resolution spectroscopy. This goes back to what John Screw was saying yesterday. JWST does nothing to us if we want high resolution spectroscopy, but it will be a great telescope for the evolution, the chemical and physical evolution of inner disks within 10 AU, as long as we can capture some of these molecules. So thank you, Luke, for your questions.
Great. There are some more questions, I believe. Regarding massive binaries, could there be disks around both stars? Maybe also a circumbinary disk?
Yeah, so I did this a little more in my talk, but some of the results I show are Lisa's, so she should also weigh in here. But yeah, so it seems like once there are cases we can point toward of each, like a binary system with only a circumbinary disk and no detectable emission around either individual star. That's COTU Tau 4. There's one where it appears there is at least a disk around the primary. I'm not sure if there's circumbinary material. That's DF Tau, but that's a system that Lisa studied in great detail. And then cases where we can see material around both. One factor we want to keep in mind is that the separation of the binary matters. Once you get outside of solar system scale, so outside of 50 AU, it seems like they much more seem to evolve independently in that they have a disk or not in accordance with how a single star like that would have a disk or not. So the interactions really only seem to start to kick in inside of a few tens of AU. And I'd turn over to Lisa if she wants to talk more about the specific systems she's studied.
Yeah, I mean, there's so many, and the thing is, we have these agglomerations of data that we can use to say something statistical, something general. But what I find very disturbing are these exceptions, and there's these strange cases. The DF Tau binary is the separation is close to this, well, a little bit less than this cutoff. I think it's about 14 AU is a semi-major axis, but the eccentricity is very high. And it appears that only one of these two stars, and they're extremely similar, they have almost the same mass, and only one of them has a circumstellar disk. There does not seem to be any circumbinary material, but it's very strange, because why would two stars of similar mass have only one disk remaining in the system? And so that raises other ideas. I mean, how does the disk get destroyed? Why does one survive? You can put the question either way. The other interesting cases are things like GG Tau, right? So the question about circumbinary and circumstellar, it's a quadruple at least, with a separation about 10 AU. And it has one component has a very close pair. I think the separation is about not 10 AU, 10 arc seconds. One pair has a 0.3 arc second separation. The other pair is a little bit wider than that. But they're a circumstellar disk and a circumbinary disk. So clearly there's a sort of a whole global picture in that system, which is very complex. Things like T Tau South is part of a triple system, but it's a very close pair with tremendous amount of circumstellar and circum-environmental material. It's a very complex dynamic environment. And the periastron on that system is only something like 3 AU. And the orbital period is somewhere around 24 years. So clearly that system has been through many, many dynamical timescales. So there are some systems that seem to retain their small disks very, very persistently. So I don't know if that actually got to the question, because I think we kind of got off on a tangent there. But yeah, there's these, when you say massive, I think most of what we're talking about in this session are things that are solar type or lower mass than that. you get into Herberg AE/BE stars. I think, Adam, you've done some more work on that.
Sorry, I missed that last part. I was trying to answer someone else's question off on the side. But anyway, yeah, so I just one piece I might add to what I said earlier is I think it's useful to have a general picture here of where mass is at and where mass is flowing from and to. And so sort of my picture is each star can have a disk, and then there's a circumbinary reservoir of material. And since small disks evolve fast, I would expect a small disk around one of the individual stars to drain onto the star and go away quickly. So I would expect that you need a reservoir in the outer disk where the evolution timescale is longer in order to be able to have a disk last for millions of years, or else it should just dump everything on the star and go away. But we keep on finding these, and we expect there to be sort of influences in terms of stuff gradually moves inward, disks gradually dump their mass downward down the potential well. And so there should probably be like a pathway to get from the outer disk to one of the individual disks around the stars. But then the stars are also like eroding away all of this. We keep on seeing exceptions to this, as Lisa pointed out, to where I can't construct a simple picture that this is what always happens. We see a disk only around one star, or a disk but not necessarily a reservoir, or only the reservoir, and the material can't find a way to get down to the individual stars. And so I think part of the story is figuring out what is different about these different binaries that explains why they don't follow the simple picture, and hoping that we have a manageable number of complicated pictures that we have to fit into this whole scheme.
Okay, let's move on to another question then. The next question says, is there any possibility of life existing in a rogue planet? Which I would like to extend to, is it possible that a disk dissipates a large fraction of the mass via scattering of planets?
I don't think that's, I think absolutely some scattering is possible, but I don't think that it's, I mean, the amount of mass in a planet, amount of mass in a disk is we talk about it as very slow, it's very small. The GG TAO system is actually one system in which we say, oh, this is one of the largest disk masses known, and the estimate is something around 0.1 solar masses, which isn't a lot. And then planets, of course, take even smaller amounts of that. So I think you need a lot of disk mass to form relatively to form larger planets. Smaller disks are likely to form smaller planets only. And so I think it's a proportionality. I think that might be a question for somebody who does more dynamical work as far as what are the expectations for planet-planet scattering. But
yeah, totally.
That's an element of a way to get rid of some material, but I think that would have to be a quite advanced stage to have already formed the planets, and so you've sort of. And once you've formed the planets, it might not be such a burning question.
Okay, let's move on. That we still have a couple, and we have also some minutes. To what extent do we expect this dust evolution timescale to map the gas dispersal timescales?
Andrea.
That's a very broad, very interesting question that can be taken from different angles, inner disk, outer disk. So, right. So yeah, we could say multiple things, and again, multiple angles. So one angle surely is one that was already covered in one of the online talks, the timescale of decrease of accretion rates and decrease of infrared excess. Those early plots showing the fraction of disks as a function of time. There is a version of that plot with the accretion rates also as a function of time. And the two curves follow similar timescales. So this is one answer to that question. So gas and dust do evolve on similar timescales. That probes the inner disk. From the point of view of the outer disk, we have seen from Karin Oberg and others earlier today that gas of disk can be way much more extended than the dust. So there are other processes there going on. The disk gas masses don't trace very well what it's supposed to be the disk mass from the dust. So there are other problems there. But in general, I would say from the point of view of the inner disk, there is multiple evidence for a close coevolution of dust and gas. And it's very much unexplored land still. So I would encourage some of the students online to get into the topic, and hopefully more models will be done explaining. We have lots of observations about the evolution of inner disks, but modeling it's extremely challenging, extremely difficult, because it's, as you have seen from our few slides, it's so complex. That region of the disk is so complex. So much is going on: winds, accretion, densities and gradients in density and temperature. It's really a mess. So it's very challenging. Yeah, just a few thoughts.
Great, thank you so much. And I think we have time for a very quick question. How does migration of planets or objects happen from one disk to another? What are the requirements for that to happen? I assume that's referring to these binaries. If there's circumstellar disks in the binaries.
Well, I was waiting to see if anyone else wants to weigh in. But if you mean the migration from one to the other, meaning like switching systems, then this is something that has been dynamically modeled in terms of being able to move, like I think the models I've seen are planets moving back and forth between binaries, and you can construct ways to make it happen. I don't know if anyone's modeled it during the disk stage when it might be a little easier, because you could like think about the disk being able to dissipate the energy from a planet, like being kicked out from one star, going by the other. You need to have some way to slow it down enough to like keep it trapped there. But I think my assumption is, given this overall trend for the average mass to move inward in disks, then probably what's happening is there isn't too much like large scale motion of large things back and forth between them, but you will scatter some number of planetesimals between the two. To the extent that I'm not sure if there's a signature of that having happened. If the two stars form at the same time out of the same overall clump of material, then their composition and age should be pretty much the same. And so I suspect if something formed around one versus the other, it'll probably look pretty similar after the fact. If you meant in terms of like how it changes in primary versus secondary, people have talked about like there are models of, do you accrete mass preferentially onto the more massive or the less massive star? But I think here there are enough knobs you can turn in terms of the mass ratio between the two stars, masses, or the eccentricity, that you can actually put mass onto either one, and then sort of turn a knob on how much planet formation you expect for one versus the other. It's one of these complications that there's no simple story. You get disks around each star and disks around both in a circumbinary configuration.
Yeah, it's probably a fairly rare, if it happens, it's probably a fairly rare occurrence that a significant amount of disk mass or planets would be flipping back and forth. But yes, as Adam said, you can set it up dynamically to make it possible. We have 1 minute, 39 seconds left according to Don's timer. So I just wanted to make one last 30-second comment that I find it very interesting that binaries are ubiquitous. Most stars are in binary systems or multiple systems, or at least half, but probably more than that. But interesting, so they are very important. It's what I do a lot of work on. They are very important, but they're not the answer completely to this. As Adam pointed out, we have disks and planets around binaries, both circumbinary and circumstellar. And there are systems that are binaries that keep their disks for many, many millions of years. So it's not like all of the things that have lost their disks that are 1 million years old are binaries. So that's part of the equation, but it's not the entire equation. And maybe it's planets, which leads me to wonder, can we find systems that do not have planets? Are there disks that TW Hydra, is that disk actively accreting disk? Is it so long-lived because there's no planets? So I just want to throw that out there. There's something else going on. It might be chemistry, it might be dust type evolution. I don't know what it is. So I'll let you guys say a few last words.
Well, I agree that's a really important question and an interesting one. Can you have zero stuff there around a star, or do you always form something, and then how much somethings? This doesn't feel like a question we can address at the disk stage, at the protoplanetary disk stage, because we can always say, well, maybe planets formed before we looked at it. And we can't address it at the planet stage, because we can always say, well, maybe there are smaller planets. Maybe everything is the size of Mars, and those are really hard to find. Maybe we make a ton of stuff that's the size of Ceres, or asteroids everywhere, and it just never coalesced into a planet. And those are really hard to find. As I think about like where to push at this next, I think debris disks seem like an interesting case, because when like even very small things colliding will make enough dust we can see. So the demographics of debris disks in binary systems versus singles, or the overall occurrence rate of debris disks, period, might tell us something about how often do you get some kind of thing that is remaining in orbit around a star, or at least two something, so they could collide and make something we can then see.
I think we need to wrap up because we need to go to the pop posters. But if Andrea, you want to